Greetings, AP Chemistry students. This is Mr. Harper, and today what we're going to begin talking about solubility equilibria. And this is chapter 16 in the new Zoomdoll textbook. And previously, you should have already read the first part of the chapter. You will notice the chapter is pretty short because this is the shortest application of equilibrium that we have talked about so far. So, if you guys remember back, chapter 17 and well, not chapter 17 and 18, I guess chapter 15 and 14 were applications of equilibrium to the behavior of acids and bases, and chapter 13 was general equilibrium. This is the last chapter we're going to talk about, which is pretty much 100% equilibrium, and then, there'll be applications and connections to free energy and electrochemistry when we get there, but this is the last and the shortest, and in my opinion, the easiest application of equilibrium that we're going to talk about, okay? And as the title says, this is all about solubility, which is really about how things dissolve in water. And throughout this chapter, really what we're talking about primarily is the action of things we would previously have considered to be insoluble. And of course, insoluble means that those things do not dissolve well in water. And just to refresh yourself, you should go back probably and look at your Nackle-Nosa rules. You guys do have to be able to look at something and say, do you expect that it's going to be soluble or not in water? And those are the things here that we're talking about. The things we would not expect to dissolve well in water are mainly what this is going to apply to. Okay? So, a brief reminder about solubility. Okay, when you guys see this word solubility, okay, if I ask you to find the solubility of something, or if the AP test asks you to find the solubility of something, solubility is the amount of a substance, okay, it is the amount of substance that can dissolve in a given quantity of solvent or solution. And this is most typically going to be measured in molarity, which is moles per liter. Okay, you're going to be finding the number of moles of something that will dissolve per liter of solution. But of course, you could have to find this in different terms. You could also have to solve for, like, solubility in grams per liter, or milligrams per liter, or milligrams per milliliter, or some other unit. But these can all be derived from molarity. Okay, also remember that when you're describing a solution in terms of the amount of solute that is dissolved, there's a couple of different adjectives you could apply to describe the solution. One, you could say that a solution is saturated, okay? And when you describe a solution as being saturated, or when a solution is described as being saturated, that means that it contains the maximum amount of dissolved solute that it can possibly hold. So you have dissolved as much as you can hold, and no more will dissolve at the point where the solution becomes saturated, okay? If a solution is unsaturated, that means it does not have the maximum amount of solute that you can possibly dissolve in it, and that you could still dissolve more before the solution becomes saturated, okay? And if a solution is supersaturated, what that means is that this is a temporary condition where you have more solute dissolved than is ordinarily possible. Now, I say here that this is a temporary, okay, so it only exists temporarily because eventually, if you have a solution that is supersaturated, the excess solute will form a precipitate, okay? So that extra stuff will fall out of solution once it becomes supersaturated. And we're going to talk about, in this unit, how to classify a solution in terms of being saturated, unsaturated, or supersaturated, and how to evaluate when a precipitate will form, when it won't form, and things of that nature, okay? And so this is really all about equilibrium, the application of equilibrium, okay? And so this is going to be, this process, the dissolving of a solid, is going to be described by an equilibrium constant. And so to kind of understand how this works, you guys read about this last night. Right now I want you guys to use your imagination. Let's imagine that I took a beaker. Okay, I can't really draw very well, so here's my loppy looking beaker, and we're going to put some water in this beaker. And then into this beaker, we're going to drop some insoluble compound. We will say that on the bottom here, we're going to put some silver bromide, whose formula is AgBr. You would expect, according to your Nackle-Nosa rules, that silver bromide would not be very soluble in water because it is the silver salt of bromide. And although halides, like bromide, are generally soluble in water, silver is an exception to that rule, and so you would expect that does not dissolve in water. Well, the reality is that everything will dissolve to a certain extent, just not necessarily a very large extent. So if you're comparing silver bromide to something like sodium bromide, okay, well, sodium bromide is something you would expect would be a soluble compound in water. And so when you put sodium bromide in water, that guy is going to thoroughly dissociate and completely change to ions. And you're going to make sodium and bromide like that, okay? Silver bromide, you wouldn't expect to do that, but it will, to a small extent, dissolve. So say that we did take this silver bromide and drop it into that beaker. Well, if you were to observe that over time, here's what you would see happen, not necessarily very fast, but here's what would happen, is that very slowly this would, to a small extent, dissolve, and as that dissolved, okay, what you would see is you would, as that dissociates, right, you would form silver ions in the solution, and you would form some bromide ions in the solution. And slowly this would happen some more, and then the concentration of silver ions and bromide ions would build up. And they would build up until, okay, what you actually would start seeing happen would be the reverse reaction also. These ions would start to reform the solid. And once these two processes, which are opposites of each other, the dissociation of silver bromide into ions, and then the recombination of these ions back into the solid, once those two things happen at the same rate, after these ions have built up to a certain concentration, then the system would be at equilibrium, okay, because the two processes will be happening at the same rate. Now here's the thing, for that solution where it is at equilibrium, then we would say that that solution is saturated, because once those two things are happening at the same rate, there will still be some silver bromide left on the bottom of the beaker. This will not all have dissolved. Some will, but there'll still be some left. And if I added more silver bromide, or if I stirred it, or if I crushed it up, or something like that, that would not affect the net amount of the salt that had dissolved in water. There's no way I could increase the concentration because it's reached the maximum that it can possibly hold, because the two rates of dissolution and then deposition of the solid would be equal, okay? Now, we could write this process like this, okay? So here's the reaction, or here's the equation, rather. So silver bromide is going to dissociate and make silver ions, okay? And bromide ions, and these, of course, could be an aqueous solution, okay? And this is right here a solid. And these two things are happening at the same rate, and so these guys are at equilibrium. And so because this is an equilibrium process, we could describe this process using an equilibrium constant, okay? And so we're going to write an expression for K, which is the equilibrium constant for that guy. Now, because here we're talking about solubility, just like with acids, when we talked about acid dissociation, we used a subscript of A to specify Ka was the ionization constant for an acid, and with a base, we put a B as a subscript to specify that's the ionization constant for a base. This, K, has a special name, and this is called a solubility product constant, okay? And the symbol is KSP. Anytime you guys see KSP, you know that's talking about the dissolution of a solid, or a solubility equilibrium, okay? Now, if we were going to write the equilibrium constant for what's going on right here, okay, it would look like this. It would be the molarity of silver ions measured at equilibrium times the molarity of bromide ions, okay? And there we go. Now you're going to notice that the silver bromide, AgBr, is not a part of that expression. And if you guys remember back a few weeks, you'll remember that the reason for that is because you don't include solids in the equilibrium constant expression, because their concentration, the ratio of moles per liter, does not change. It's just the ions that change, okay? And so that's my KSP expression. And so if I was able to measure the concentrations of these ions at equilibrium, I could calculate an equilibrium constant for the process, okay? And it turns out that I can, in fact, measure those things, and if I do, that the molarity of silver ions would be equal to the molarity of bromide ions, since they're produced in a 1-to-1 ratio, and that is 5.7 times 10 to the minus 7th power molar. And so once the solid has dissociated, and once these ions have built up to that concentration, the system is going to be at equilibrium, and now I could use that to calculate the value of KSP. If I plug this in for silver, and if I plug it in for bromide, and I calculate the value, what I'm going to get is something like 3.3 times 10 to the minus 13th power molar, okay? And that's how you calculate the equilibrium constant for this process. Now, if you look here at the value of K, you guys are going to notice that this is a very small value. And what that tells you is that for this substance, the position of equilibrium lies to the left. It is reactant favored, and that's because silver bromide is an insoluble compound. It does not dissolve well in water. But even things that are very poorly soluble will dissolve to a very small degree. Okay? If you contrast what we just found for silver bromide, okay, which is that, with what you see for sodium bromide, which is a soluble compound, right? Well, this reaction is also, in principle, reversible, but the position of equilibrium lies far to the right. And so if you were going to calculate an equilibrium constant for that process, that's going to be a big number. So for your soluble compounds, which you would predict to dissolve in water according to the Nakalnoso rules, they're going to have big equilibrium constants that will dissolve well and are going to be product favored. But for everything we're going to pretty much do math with in this chapter, it's going to be like this, where you have small equilibrium constants and it is reactant favored. And so hopefully that idea, what this tells you and what it is, makes sense, because we're now going to use it to do various things, okay? But first, some practice writing the expressions for KSP, okay? Because these can be a little bit tricky. Anytime that the math goes off the rails, a lot of times it's with writing KSP incorrectly. So we'll do a couple of examples, okay? You guys are going to, with your partner, do two of these yourselves. I'll show you guys here one really quick. For barium, actually, no, we'll look at the last one, silver carbonate, because that one's more difficult, okay? So we're going to write the expression, KSP, for these dissolutions. Now, silver carbonate, when that dissolves in water, is going to do this, right? It's going to be a reversible process. And when this dissociates, the ions split apart entirely. And if you look, the formula says we got two silver ions there, so we're going to make two Ag plus ions, and we're going to make a single carbonate, CO3 2 minus. Now, if I write the equilibrium constant, KSP, for that process, right, this is going to be, we're not going to include the silver carbonate because this baby here is a solid, which is dissolving in water. Okay, and these two ions are aqueous. So we're not going to include the solid. We are going to include the ions. This would be the molarity at equilibrium of silver ions squared times the molarity of carbonate ions to the first power. And of course, getting back to what we learned about equilibrium in the first place, right? This exponent of 2 comes from that guy right there. Because we have two silver ions, that there becomes the power to which the molarity of silver is raised. And there we go. I want you guys to pause the podcast here really quick and then do the other two with your partner, and I'll show you the answers. Pause. Okay, and we're back. For barium sulfate, if you write the reaction or the equation for the dissolution, right, this dissociates. You get barium ions, which are a 2 plus ion, and you get sulfate ions, which are 2 minus, okay? And the KSP expression looks like this. KSP is going to be equal to the molarity of barium ions times the molarity of sulfate ions, okay? For this guy right here, which is bismuth iodide, when this dissociates in water, I'm going to get a bismuth ion, Bi3+. I'm going to get 3 iodide ions. If I write the KSP expression for this guy, it looks like this. KSP is equal to the molarity of bismuth times the molarity of iodide, I minus, cubed. And there we go. Easy stuff, but it bears reviewing. Now, we're going to look at a couple important applications. The first one is, if I have data, how do I calculate KSP? And so we're going to do a couple examples here. Okay, here's the first one. It says we're going to find the KSP value for silver iodide, which is AgI. Okay, and it tells me that the solubility of silver iodide is 1.22 times 10 to the minus 8th molar at 25 degrees Celsius. Okay, and we're going to find the equilibrium constant for that, for the dissolution of silver iodide. The first thing we want to do probably is write down what the equilibrium is, right? So silver iodide is an insoluble compound. If you drop it in water, it is primarily going to be a solid, and it is going to a small degree ionize and form silver plus, okay, and iodide. Now, here's what this means here. It says the solubility is 1.22 times 10 to the minus 8th power molar, okay, at 25 degrees Celsius. This, by the way, is affected by temperature. I didn't mention that before. I meant to. When you think about things that affect solubility, right, temperature is one thing that affects solubility, okay, and that also is going to affect the value of the equilibrium constant, which describes to what extent the thing dissolves. But in any case, what this tells you is that for silver iodide, 1.822 times 10 to the minus 8th power moles of that will dissolve per liter of the solution, okay? And so, if I think about what goes on here, right, okay, like when we're considering solubility equilibrium, we don't really care about the solid because that doesn't affect the equilibrium, right? And so when I just toss silver iodide in water, I don't have any of these things to start with, and that tells me that when that this much of that stuff can dissolve, or in other words, that the solution becomes saturated when 1.22 times 10 to the minus 8th power moles of that has dissolved per liter. Now here's what that means. You can see here if you look at the formula, silver iodide, that AgI contains, for each mole of silver iodide that dissolves, you get 1 mole of silver ions and 1 mole of iodide. I'm going to say that again. If you look here at the formula of silver iodide, there's a 1-to-1 ratio, right? For 1 mole of silver iodide, the compound, you produce 1 mole of silver ions, and you produce 1 mole of iodide ions. And so if this right here is the solubility, right, or the amount of silver iodide that dissolves, that tells you that the equilibrium concentration of silver ions is likewise going to be 1.22 times 10 to the minus 8th power molar, as is the concentration of iodide ions. That will also be 1.22 times 10 to the minus 8th power molar. And the reason for that, okay, is because these things are both produced in equal amounts when this dissolves in a 1-to-1 ratio, okay? And so, since I know from the solubility what the concentration of the ions is in solution, I can then go through and calculate the value of the equilibrium constant. KSP is going to be equal to the molarity of silver ions times the molarity of iodide ions, which is just going to be this number right here, 1.22 times 10 to the minus 8th power molar squared. And if you plug in your numbers and do the calculation, you get 1.49 times 10 to the minus 16th power. And there you go. Okay? Let's do another one. Example 2. This one says we're going to calculate KSP for this guy, lead 2 chloride. The formula, by the way, for lead 2 chloride is PbCl2. Okay? It says if the lead ion concentration in a saturated solution is found to be 1.62 times 10 to the minus 2nd power molar. Okay? So let's think about lead chloride. If I take solid lead chloride, which is PbCl2, and I just put it in water and allow it to come to equilibrium, what it's going to do, this of course being solid, is going to ionize, it's going to dissociate, and we're going to produce lead 2 plus, Pb2 plus, and then we're going to produce chloride, 2 chloride ions, right? And so, I'm going to make an ions table to describe the equilibrium, okay? Before any dissolution happens, the concentration of lead and chloride is both 0, okay? And then it tells me here that in a saturated solution, now when you hear saturated, that means the solution has come to equilibrium. So lead chloride has dissolved in water until it can't dissolve anymore, and it's been found that the concentration of lead ions is 1.62 times 10 to the minus 2nd power molar. Well, here's the thing. If all the ions in the solution are coming just from lead chloride dissolving, right? Well, I can see from the equation that I produce twice as many chloride ions as I produce lead ions, which means that at equilibrium, the concentration of chloride must be double that of lead. Or in other words, this is going to have to be 3.24 times 10 to the minus 2nd power molar there for chloride, okay? And that's just because of the stoichiometry. It's because I produce twice as much of those, or twice the concentration of those, as I produce lead. And so now that I know the concentrations of the ions, I can set up my KSP expression and plug in the numbers. Now here's the trick. KSP, okay, for this one's a little more complex because we got that coefficient of 2 right there. And so KSP is going to be equal to the molarity of lead 2 plus ions times the molarity of chloride ions squared. if we take our information, we plug it in, so that's my concentration of lead, and that's my concentration of chloride. If you go through and plug it in your calculators and calculate, I'll pause a second while you do that, then I'll keep talking to waste time so that you guys can plug in your calculators and you can put it in, and you can see that the KSP value is going to be equal to 1.7 times 10 to the minus fifth power. And there we go. Okay, so that's how you guys calculate KSP from data. That's easy stuff. Now, we can also do the reverse process. I just showed you guys how to calculate KSP values if you know the solubility, but one of the big applications of having these equilibrium constants is I can use a KSP value to estimate what the solubility of a compound is going to be. And here I'm saying that we can estimate the solubility, and the reason why is because when we look at the solubility equilibrium right here, like I've written down here on this page, we're making kind of an assumption. We're assuming that when I drop my lead chloride into water or whatever the compound may be, that it simply ionizes and simply dissociates into its constituent ions. And as you guys are going to see, that is not always the case. There's sometimes more than one thing that goes on, but we're going to ignore that for right now. So treat what we're going to do next as kind of approximate as opposed to exact. Okay? So here's how to estimate the solubility. The easiest way is to do an example. Okay? So this one says that we're going to find the solubility of calcium carbonate, another insoluble ionic compound, in water in moles per liter if the KSP value is that at a certain temperature. Okay, so if calcium carbonate dissolves, here's what that looks like. Okay, this is a relatively insoluble compound. It's going to dissociate in water, and it's going to form calcium ions and carbonate ions. Okay, if we set up an ice table, we know that the solid is not going to change, and so we just kind of ignore that. And then the calcium starts at 0 and the carbonate starts at 0, assuming, of course, that the only source of ions is the calcium carbonate sitting there in water and dissolving. Now, if I want to figure out the solubility of calcium carbonate, well, really what that's saying is what is the maximum concentration of calcium carbonate that can dissolve in the water before it reaches equilibrium and becomes saturated. And so to do that, I'm going to figure out, well, what is my equilibrium concentration of calcium ions and carbonate? And to do that, we just set up the ice table, and we say that, well, as this thing dissociates in water, it's going to produce calcium. We don't know how much, and so we're going to call that number x. So the change there is going to be x. This is going to likewise go up by x, and so at equilibrium, we're going to have x calcium ions and x carbonate ions. And if I want to now find the value of x, I'm just going to use the KSP expression. KSP for calcium carbonate is going to be equal to the equilibrium concentration of calcium ions, right, times the equilibrium concentration of carbonate ions. Okay, since both of these are x, KSP is going to be equal to x squared. The value of KSP, we've already seen, is given up there. It's 3.8 times 10 to the minus 9th power. And so to find the concentrations, I just solve for x. If I do that, I find that x is going to be equal to 6.16 times 10 to the minus 5th power molar. And ladies and gentlemen, that is going to be the solubility of calcium carbonate. Now, here's how, wait a minute, Mr. Harper. This is, I just thought, the concentration of carbonate and the concentration of calcium ions here from the ice table. Well, that's true. But this is identical to the molar solubility of the compound. And the reason why is because, notice that when this dissolves, it's a 1-to-1 mole ratio. 1 mole of this produces 1 mole of calcium. 1 mole of this produces 1 mole of carbonate. And so the molar solubility of calcium carbonate is going to be the same value as the molarity of the ions at equilibrium. Okay, let's do one that's a little bit more difficult. Okay, so we're going to find the solubility of this guy, magnesium fluoride, using its KSP value. Okay, magnesium fluoride, if you guys remember, magnesium is a 2+ ion, and fluoride, of course, is a 1-. F- is what you don't want in chemistry. And so this guy's formula is MgF2. MgF2 You know, actually, if you guys use your Nakamoto rules, you'd probably expect magnesium fluoride to be soluble in water, but it's not. There are some exceptions that are not covered by those rules. I know they're just rough, easy guidelines for you guys to remember, but it turns out that magnesium fluoride and also calcium fluoride are not very soluble in water. Those are some exceptions I don't have you guys memorized because they don't come up very often, but there you go, okay? So this is a solid, okay? It's going to ionize in water, and we're going to get magnesium ions, Mg2+, and then we're going to get 2 fluorides, 2F minus, okay? I want to find the solubility of that compound, and so in order to do that, we're going to do what we did in the last problem, and we're going to go through and solve for the equilibrium concentrations of these 2 ions right here. And so we're going to set up our ice table, and we're going to think about what happens, okay? We don't care about magnesium fluoride, we just care about these. This starts the concentration of 0, and that starts at 0. In this case, because we're assuming that the only source of magnesium and fluoride ions is the original ionic compound. Okay? As these guys approach equilibrium, this is going to increase the concentration by X. Now, here's the tricky thing. The fluoride concentration doesn't go up by X, it goes up by 2X. Okay? And so now, at equilibrium, this is going to be X, and this concentration is going to be 2X. In order to find the value of X, now I've got to set up my equilibrium constant expression. KSP for this compound is going to be equal to the molarity of Mg2 plus ions times the molarity of fluoride ions squared. And this is where it's easy to make an easy mistake, is in these sort of things, setting up the equilibrium constant thing, because here's the trick. The concentration of magnesium is X at equilibrium. The concentration of fluoride is 2X. That whole quantity squared. And so if you go through and do this, 2x quantity squared is 4x squared times x is 4x cubed, right? And so since that's what KSP is, right, this is 4x cubed. Now we're going to set that equal to the value for the equilibrium constant, which is 6.4 times 10 to the minus 9th power. And now we go through and solve for x. If you go through and solve for x, we can divide both sides by 4, take the cube root, and so x is going to be equal to whatever it is, something like 0.00117 molar. Okay? Yeah. Okay? So there is the molarity, okay, or actually, let's round this to the correct number of significant figures here, because if you look at our equilibrium constant, it's only got 2, and so they're going to have 0.0012 molar is going to be the value of X. So I'm going to change pen color here, okay? So once equilibrium has been established, that means that the molarity of magnesium ions is going to be 0.0012 molar, and for fluoride, it's going to be 0.0024 molar, or moles per liter, okay? Now, those are my ion concentrations at equilibrium, but that's not really what the question's asking, right? It's asking me to calculate the solubility of magnesium fluoride. And so we need to know what that is. Well, we can find that from the ion concentrations. It turns out that the solubility of magnesium fluoride is 0.0012 molar, or 0.0012 moles per liter. And you say, well, Mr. Harper, why is that? We have these 2 ion concentrations down here, and you're saying that the solubility of the compound is equal just to the concentration of magnesium, but not fluoride. Why, Mr. Harper, is that? Well, here's the way to think about it. In order to get these equilibrium concentrations, like that concentration and that concentration right there, in order for that to happen, 0.0012 moles of magnesium fluoride had to dissolve per liter of solution. Because when 1 mole of this dissolves, we make 1 mole of magnesium ions and 2 moles of fluoride ions. Okay? So it's a 1-to-1 ratio going from magnesium fluoride to magnesium ion, and it's a 1-to-2 ratio going from magnesium fluoride to F minus. So the equilibrium concentration of F minus is double what of this dissolved, right? And if we think about the magnesium ion concentration, because it's a 1-to-1 ratio, the concentration of magnesium ions at equilibrium is equal to the concentration of this that dissolved. And so that's why that's the molar solubility of that compound in water at equilibrium. If you guys require further explanation of this topic, then you guys should consult your textbook over the weekend. So, ladies and gentlemen, that is going to be the end of notes for today. I hope you found this illuminating. We're just looking at these two topics today, how to calculate a value of KSP and how to estimate solubility from KSP. Later on, we're going to talk about the common ion effect and how that affects solubility compounds. We'll talk about simultaneous equilibria, other things that happen at the same time as an ionic compound dissolving, which can influence the solubility of a compound. Like, I'll give you a hint. For this guy right here, okay, we estimated the solubility to be this. It's actually going to be higher. And I'll tell you why as a preview. Now, don't let this confuse you for the homework tonight, but you see this guy here, F minus? From the last unit, you guys should recognize something about that. F minus is a weak base, the conjugate base of hydrofluoric acid. And so, in this problem, we're assuming the only thing going on is magnesium fluoride. This ionic compound dissolves and makes these ions, and that they just sit there in water and nothing else happens. Well, really, this fluoride ion, once formed, is then going to go on to react with water, right, and is going to be in equilibrium and is going to create FHF and hydroxide, right? And so, in that process, fluoride gets used up, which means that this concentration is going to decrease, and it's going to shift the position of equilibrium to the right, and it's going to be more soluble than we expect. We'll talk more about that later on. Just a preview, okay? So that's that. Hope that's been intelligible. This is going to be posted on YouTube, and so you guys can watch it again if you guys have questions. Please apply yourselves fully to the homework, because here's a horrifying proposition. After today, guys, there's only 20 days until the AP exam. 20 school days till the AP exam. And so have yourselves a nice weekend, do the problems, and I will see you on Monday. Goodbye.